Okay, so this is the last lecture, the fourth lecture in Unit 4 in our thermochemistry lecture, and it's going to focus on some of the last little odds and ends of how things fit together and what's left for us conceptually in this unit, as well as calculations. So you're going to start with thermochemistry, and then there are some other things that will come into play as well that kind of tie together a lot of what we've already talked about. So if you haven't done so already, you need to stop the video here and do the learning targets. Notice that some of them are from your book, some of them are not, and some of them are actually from chapter 16 in your book. So make sure that you're finding the right pages. When you're finished with this part, you can restart the video and add to what you have as you watch the rest. Okay, so let's go. So thermostoichiometry is really just like any other stoichiometry. Basically, what happens is that our thermochemical equations have coefficients that correspond to that specific delta H that is either determined through calorimetry or another way that goes with that reaction as it's written. So the coefficients are really, really important, and this is hammered home from Hess's law and from a few other things that we do, but the amount that's shown in the equation would be in moles using the coefficients, and the amount of heat that matches it in our thermochemical equation has to match those coefficients in numbers of moles. So it's really pretty straightforward. It's like doing stoichiometry for anything else. You're going to convert to moles, and then you're going to transfer to heat, or you might be given heat and use the mole ratio to convert to moles of a substance and then back out to grams if that's what you're asked for. We can do this with a lot of different things, so I picked a question that is from your book just to use as an illustration. So in a lightning bolt, nitrogen and oxygen form nitrogen monoxide, and we definitely need a chemical reaction for this. They tell us how much heat is absorbed per mole of N2, so we want to make sure that that matches. So I'm going to go ahead and write the equation for this. We have N2 plus O2, nitrogen and oxygen, remember that those are both diatomic, forms NO, and I need to balance that equation, so I need to use 2 moles of NO, and that will take care of that. And then I'm going to read to make sure that I know what delta H matches. And this says delta H is for 1 mole of N2 reacting, which is the coefficient that I already have. It absorbs, so that's a positive delta H, 180.58 kilojoules of heat. So once I've decided that this is per mole of N2, if it had been per mole of NO, I would have had to divide my equation in half to make it match that delta H. But now because my mole of N2 is already 1 mole in my equation, it matches. So here's my thermochemical equation. That's a little bit of review. And they want to know if how much heat is absorbed if 3.5 metric tons of nitrogen monoxide forms. So they give you some conversions here about metric tons and kilograms, and so we'll have to use that. This is just complicated only for that reason. So I'm going to start with my 3.50 metric tons. I probably should use the same abbreviation they use. They're calling them T's. I'm going to call it MTs. And I need to get that of, let's see, this is of NO forming. So I need to get that to grams of NO to moles of NO so that I can use my coefficients in my equation. So metric tons of NO to kilograms, they gave me in a conversion. They said that 1 metric ton is equal to 10 to the third kilograms. And so then I can use kilograms of NO to get to grams of NO, and that would be 1 kilogram is 1,000 grams. And then finally, I can use the molar mass of NO to get to moles of NO. And that was the whole beginning step. Remember, in stoichiometry, your first process is always to get what you need, what you were given, into moles. So 1 mole of NO, and from the periodic table, I used 30.01 grams as the molar mass. So now I have moles of NO, and I can use the coefficients in my equation, the NO's coefficient with the heat, to go from moles of NO to how much heat is absorbed. So I have moles of NO two of them from my equation, equals to or is equivalent to 180.58 kilojoules, that delta H. Okay, so this is it. When I cancel out the units that cancel, metric tons cancel, kilograms cancel, grams cancel, moles cancel, and I have kilojoules. So I can come back in and do my math, and I get a humongous number, which actually should make sense because this is a really large amount of nitrogen monoxide forming in our clouds, in our lightning bolt. And so I get 105,303.23. That's a huge number, 0.23 kilojoules. And I have to come back and look at significant figures. So the delta H they gave me has lots of sig figs, but my metric tons is 3.5. So I need to round that to 3 significant figures. I'm going to put this in scientific notation. It will be easier. 1.05 times 10 to the 7 times 10 to the 7th kilojoules of heat. So that's how you use the delta H with a thermochemical equation to do stoichiometry. That's that example. Okay, so now we're going to shift gears a little bit. That gets you through this part about thermochemical equivalence and an example in thermochem. So we've done that part. Let's come and look at standard and what does that tell us, and standard enthalpy of formation, etc. Okay, so some things that are super important is that in thermochem, standard conditions, so you have to be careful whether they're talking about conditions or standard state. But in thermochem, standard conditions are 1 atmosphere for gases, just like it was in gas laws. But for everything in thermochem, even gases, standard temperature is 25 degrees Celsius. This is a big difference because we just finished gas laws where in gas laws standard temperature is 0 Celsius. So when we talk about anything in thermochem or thermodynamics or electrochem or equilibrium, any of these things that we'll do later, we talk about at 25 degrees Celsius for standard. All right, so this is important that you think about that. We also need to know that in standard, we're talking about gases that are behaving ideally, and we're talking about solutions that are 1 molar in concentration, and we're talking about substances being in the state of matter that they should be at 1 atmosphere and 25 degrees Celsius. Okay, standard enthalpy of formation is a definition of a substance. So it's basically telling us the change in heat required or given off, either absorbed or given off, when 1 mole of a compound is formed from its elements in their standard states. This is a really important definition. Okay, the standard enthalpy of formation has 3 parts. It has to include 1 mole of the compound forming, it has to form only from their elements, and the elements have to be in their standard states. Okay, something that you will have to know on College Board's exam is that the heat of formation of elements in their standard states is 0 kilojoules per mole. You have to know that because you don't have a table of reference on the AP exam, and so they'll include what you need reference-wise in the questions, but they will never give you a standard heat of formation for an element. And I want you to picture that they really are reference, that if our elements are in their standard state, they should just be already formed. We shouldn't have to add energy to them or remove energy from them to make them form. And so this is why there are reference at 0 kilojoules per mole. And then anything else that's different. So if it wasn't in its standard state, if we were talking about liquid nitrogen instead of nitrogen gas, then to make liquid nitrogen, we have to remove energy. So it would be a negative heat of formation for liquid nitrogen. So I just kind of want you to think about that relationship. But that's really important that you understand that, and that you can picture that if you were looking it up, you would find the standard heat of formation of elements being 0 kilojoules per mole. So we're going to practice this definition just a little bit, and I'm going to write a few formation equations with you. Remember that a formation equation is going to represent forming 1 mole of a compound from its elements in their standard states. And so I'm going to do the first one here, and then I think I'll have to add a page. But we're going to form CH3OH, liquid, from its elements in their standard states. So the elements that we have that form this, actually I need to move this over, I think. From the elements that we have that form this, we would have carbon, which is not diatomic. We would have hydrogen, which is diatomic. And we would have oxygen, that is diatomic. Okay? And now I need to balance the equation. So I see that I have 2 O's on the left and 1 on the right, which means I'm going to have to double my CH3OH. And that will take care of the O's, but now I have 2 carbon. And then I have 8 oxygen, so I need to put a 4 in front, or sorry, hydrogen, so I need to put a 4 in front of the hydrogen. This is a formation equation, but it is not a standard formation equation because we're not forming 1 mole. So to form 1 mole, we're going to have to divide it all by 2. And that will give me carbon. And oh, by the way, carbon's standard state would be solid. And that would give me 4 divided by 2 is 2 hydrogen, and hydrogen's standard state is gas. And 1 divided by 2 would be 1/2 O2s, and in thermochem it's not unusual to see those fractions, and it would be gas. And it's going to form 2 divided by 1, or 2 divided by 2 is 1, CH3OH liquid. Okay, so my formation equation is this, and I kind of ran out of room, so it takes 2 lines. And the value of delta HF, or standard heat of formation, that degree sign is standard, and this is formation. Okay, so the standard enthalpy or standard heat of formation for this in kilojoules per mole, I would look up off of the thermodynamics chart. I pulled this one from the back of your book as negative standard heat of formation would be negative 238.6 kilojoules. Okay, so if you need another couple of examples, I'll come back at the end of the video, or actually I will just maybe post a quick whatever. I don't think we need more examples. I put 2 more on here, but I think we're okay. So if you need more examples, then you can definitely ask for help afterwards, and we'll go from there. But remember, you're forming 1 mole of your compound from the elements that make it up in their standard states, and then you can look up the value for standard heat of formation from your thermodynamics table. And if you want more practice, then you can stop this and practice and go check it and see what you think, because this is in your textbook. Okay, this was example, I don't remember from your book, actually. So I should have written that down. So let's go see. Calculating delta H of reaction from standard heat of formation. So this is another way that we can calculate the heat of reaction when we're given our thermodynamics tables. So you'll see here that I included thermodynamics tables from the back of your book. This is the stuff in Appendix B in your book, and I will give you a paper copy of that chart to use. And if it's on a test or if it's on the College Board exam, then they will put this information into your information in the question. Okay, so the way that this works is that we can use basically Hess's law and the sum of the standard heats of formation of your products and your reactants, and then find the difference between them to find out the overall heat of reaction. And your book walks you through the derivation of this, but it's pretty cumbersome, and mostly I just really like that you know how to do it. So if you want that, you can go back to your book and follow through that again, but I'm okay with you doing it this way. One thing that you should get used to in thermochem is including units and including formulas, because it's really important that somebody knows how you went about this. So in this case, we want to calculate heat of reaction from the heat of formation values that we were given. So they gave us the equation, and notice that it's already balanced, and we're going to do the sum of the heats of formation of the products minus the sum of the heats of formation of the reactants. And we have to include our coefficients here as these, actually this should be an N, all right, as these numbers of moles. All right, I just noticed that from your book. That's a typo. So heat of reaction, standard heat of reaction, is equal to the sum of the standard heats of formation of the products minus the sum of the standard heats of formation of the reactants. And I'm going to set this up. Products first. This is a really big place that you make mistakes. So remember that you have to do products first. It's always final minus initial. And that would be, for the products, 4 moles of H3PO4 liquid times the standard heat of formation of H3PO4 liquid. I have to be really careful and make sure that I use the liquid, not the aqueous. Okay, so that would be negative 1,271.7 kilojoules. So times negative 1271.7 kilojoules. And that's my only product. Minus, for the reactants, 1 mole of P4O10 times the standard heat of formation of P4O10 solid here. So times negative 2984 kilojoules. Oh, this is kilojoules per mole. Sorry for these. Negative 2984 kilojoules per mole. Plus the other reactant, that would be 6 moles of water liquid. So make sure that you look for the right one here, water liquid, times negative 285.840 kilojoules per mole. And that would be my reactants. So unfortunately, I didn't have enough space to write this all out in one line. This is not hard, but it definitely has places where you can make mistakes, and it's usually in calculator punching. So be really, really careful when you punch this, and you can see that the standard heat of reaction in this case would be 4 times negative 1271.7 minus negative 2984 plus 6 times negative 285.84, and when I did all of that, I got negative 387.76, and I need to check sig figs. This is largely addition and subtraction, and everything that they gave me, oh, this was only to a whole number, so I need to round that to the whole number, which would actually be negative 388. The units are now kilojoules because we multiplied by moles to get rid of it. And this is my kilojoules. So technically, I could write a thermodynamic equation by saying delta H for this reaction is negative 388 kilojoules. Okay, so this is how we find heat of reaction from standard heats of formation. We'll do some practice like this, but something that College Board likes to do a lot is that they really like to give you the delta H for the reaction and ask you to find one of the standard heats of formation and then not put it in the chart. Okay, so this is very similar to the way a College Board question would look for this. And as soon as you realize that you know delta H and they want you to worry about something with standard heat of formation, you're going to need to use that formula of standard heat of reaction equals the sum of the standard heats of formation of the products minus the sum of the standard heats of formation of the reactants. One of the things that we'll do later in this unit is practice how you decide which method to use, what you're given, what that determines for you, etc., because there are so many different ways to do these problems that is actually one of the biggest challenges. So we'll practice that some in class, but in this case, because we have standard heat of formation, this is going to be our process. So let's look at what we know. We actually know the standard heat of reaction, so I'm going to substitute that in, negative 638.6 kilojoules equals the sum of heats of formation of the products. So my products are the carbon dioxide, gas, and they give me the standard heat of formation of that here, and I have 1 mole. So this would be 1 mole times negative 393.5 kilojoules per mole, plus my other product, which is the water vapor. So that's going to be the water vapor value that they give me here. So that would be 2 moles of water vapor times the standard heat of formation of water vapor, which is negative 241.826 kilojoules per mole. And that's my products, minus the sum of the reactants. So this is going to be 1 mole of CH3OH times the standard heat of formation of methanol, which we don't know. So this is basically my X, okay? And the other reactant is 3/2 of a mole of O2, and they don't give me the standard heat of formation of O2. So remember that O2 is gas at standard temperature and pressure for thermodynamics. And so this value you have to know as 0 kilojoules per mole. It is an element in its standard state. So this is why that is 0 and it's not on your chart. This is very typical. All right. So now I have everything left, everything filled in except for my x that I need to solve for, and I'm done with the chemistry. The only thing remaining now is the algebra. So you have to be really, really careful as you solve these. But when I do this algebraically, I should get the standard heat of formation of methanol equals negative 238.552. I look at what they've given me. My values all have 1 decimal place, except for that with 3, so I'm going to keep 1 decimal place, which is negative 238.6. And the units on standard heat of formation in there will solve out to kilojoules per mole. Okay, so this is backwards of what we did here. And it's really common that College Board does these this way. So just make sure that you're practicing this when we go to practice. Okay, so we come back up here and we've covered the ideas of all of this, I think. And so now I want to just add some odds and ends, and they won't take long. There's some terminology that you need to get used to, and this would be molar heat or standard heat. Usually it's called molar, right? So I think up here, actually, I didn't add molar in front, but almost always these are molar heats of combustion or molar heats of solution, etc. So standard actually is not a very good way to say this because combusting, we're not going to probably be at 25 degrees Celsius. So we have to be careful about that, but we can definitely talk about this as in molar. So these are definitions. These are the ideas of the amount of heat transferred, and if it's a combustion, it's going to be released, right? When 1 mole of a substance is combusted. So let's say, combusted. So let's say that we want to do this for the molar heat of combustion of methane, right? So an example for methane, it's molar heat of combustion. The equation that would represent that would be methane, and to combust it we have to add O2, and we're going to get carbon dioxide and water, and we should technically put in our states of matter here because we know that they make a difference. All right, methane is a gas. And so if we're going to write that equation, it's got to be the 1 mole of a substance combusting. Okay, so I need to balance this equation and see what I get. So I have 1 carbon and 4 hydrogen, and that gives me 2 for oxygen. So this comes with 1 mole here. But if I had chosen a different substance and this wasn't 1 mole, I would need to divide the equation by whatever that coefficient is, usually a 2, to make this represent the molar heat of combustion of methane. So the idea would be is that delta H of reaction for that equation would be the molar heat of combustion of methane, because it is the delta H for the reaction describing the heat of describing the combustion of 1 mole of methane. The same works for neutralization. So let's do an example for neutralization. This would be 1 mole, the amount of heat. Let me start over. The amount of heat transferred when 1 mole of an acid or base, and you have to decide which one you're looking at, is neutralized in an acid-base reaction. So I'm going to do an example for the neutralization of sodium hydroxide by sulfuric acid, because this will be one that we have to think about, right? So I have NaOH and H2SO4, and in a neutralization, I'm going to get water, and the salt I'm going to get in this case is Na2SO4. And I need to balance this equation. So I actually need 2 sodium hydroxides, and that's going to form 2 waters. Notice that if I want this to be the molar heat of neutralization of my sodium hydroxide, that coefficient is a 2. So I need to come back in and divide them all by 2 to give me NaOH plus 1/2 H2SO4 yields 1 water and 1/2 Na2SO4. And the delta H for that reaction would be the molar heat of neutralization of the sodium hydroxide. if I had done this for the sulfuric acid, because it's already got 1 mole, so if I had done this for the molar heat of neutralization of sulfuric acid, I wouldn't have had to divide by 2. All right, so you have to be really careful. You need your coefficient in here to be 1 mole. Finally, the last thing would be for heat of solution. So this is the same idea. This is the amount of heat transferred, and sometimes they're endothermic and sometimes they're exothermic, when 1 mole of a substance dissolves. And so, for example, maybe I want to do this for sodium chloride, dissolving into its ions. I didn't do states of matter in my equation up above, and I should have, sorry. And this would be solid sodium chloride. All right, so this is 1 mole here, so this is all good to go, but it would have to be 1 mole, and so this is kind of how we look at this. So that should clarify those definitions for molar heats of specific kinds of reactions. So just kind of think carefully about what those words mean. All right, the last thing is that this comes from actually kinetics, but we can look at this for finding delta H of reaction another way. So here we go again with another way to find heat of reaction. And so this one would be from potential energy diagrams. So notice that our y-axis is potential energy and our x-axis is time or reaction progress. And in this case, there are no numbers here, so I can't actually quantify it. But if we wanted you to find and quantify delta H of reaction from this, we would have these axes labeled, right? So notice that heat of reaction is the potential energy of the products minus that of the reactants. And so I can look at this in this case and go, whatever this value is, x, minus whatever this value is, y, would give me the heat of reaction. And so in this case, it would be x minus y. And this reaction, the stuff is gaining energy. So this one is endothermic. And in this case, delta H of reaction would be positive. Okay. And in the other case, over here, my stuff has less energy than it did at the beginning. And so if I did delta H was x minus y in this case, final minus initial, x minus y. In this case, delta H of reaction for this one would be negative, and this one is exothermic. So this is another way that we can find delta H, right? Just so that you can see, I will give you a paper copy of this. I put this in here so that you have it. It is at the end of your textbook in Appendix B, which is linked in your chapter so that it's easy to find, but it's kind of a pain. So I'm going to give you a paper copy of it, and remember that any question that you have on College Board or on my test will include the information from that chart that you would need. So I think that we have covered all of this. So that's this lecture, the final lecture in Unit 4, and we'll start to practice.